Hello, fam. This lesson is the first part of lesson 63. We're coming out of lesson 62, which has to do with constructing confidence intervals for proportions. So if I go back a little bit, you can't see that, let me fix it. We have been looking at confidence intervals for P and constructing one sample Z intervals for P, which means that all of our confidence intervals were percents. So all of the things that we were estimating were population proportion, which is a percent, which means we're dealing with categorical data. So in this case, it is, are you willing to run a very yellow light? That the categories would be yes and no. Here, what proportion, say football is their favorite sport to watch on TV, so your categories would be football, basketball, baseball, soccer, all of the televised sports. And this one has to do with the percent of bills that had or received a discount. So the categories would be, did we receive a discount, yes or no. So these are all proportions. We're calculating a percent, and we're dealing with categorical data. What we're now transitioning to is confidence intervals for a mean. So we're going to be talking about quantitative data, data that can be averaged. We can find an average value. Well, just like in sampling distributions, the method for finding a confidence interval for a mean is slightly different than the method for calculating a confidence interval for a proportion. That's why we do them in two separate lessons. So lesson 62 was proportions, lesson 63 is means, and that is where we begin on page 16 that is labeled the trouble with estimating a population mean. I have already written the notes that go on this page, which is why you see just the heading with blank paper over it, because I think to some extent this would be easier for you if you hear me explain it and then you pause the video and copy down the notes, especially when we get to question 5. So I've written all the notes and I'm just going to uncover them as we walk through it. You will pause and take the time that you need to write things down. So yeah, let's get started. So the prompt is, Miss Odell wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. So I want to know if they're giving us as much Oreo as they're saying they're giving us, and I am measuring that by weight. So I select a random sample of 30 cookies. I guess I should tell some of you guys that my maiden name is Odell. That's why I'm referring to myself. I select a random sample of 30 cookies and found the weight of each one in grams. So I have my little science scale and I take each little Oreo and I weigh it. The mean weight, so I take those 30 cookies, I add them up, divide by 30, the mean weight is 11.1921 grams. And the standard deviation of my sample is 0.0817 grams. We're supposed to make a 95% confidence interval to estimate the true mean weight of an Oreo. From last lesson, I hope that you guys are not surprised when I say there are some conditions that we need to check before we can construct a confidence interval. And that is what the following questions are based around. So question 1 is, what is the point estimate for the true mean? So remember, true mean is mu. What is our estimate for mu? Well, our estimate is what I got in my sample. I took a sample to estimate the true average weight. So my estimate is 11.1921. Okay, pause. I can't find my pen. That's why I'm looking like I don't know what I'm doing. Okay, I'm back. It was on my lap. I have often joked with my classes. I once taught the same set of kids for 5 years in a row, from 7th grade to, for some of them, their senior year. I once taught them every year. We would joke about the fact that I would spend like half of my class periods looking around for the right color pen that I wanted to use. So it's still happening. I was just looking for my black pen. Anyways, you guys probably don't care. So getting on with the show. What is the point estimate for the true mean? So our point estimate is the average of the 30 cookies that I weighed. So my estimate for true mu is 11.19. Was the sample a random sample, and why is this important? So was the sample random? Yes. Why is this important? Because random samples allow us to make inferences about the population. So without a random sample, I can't use this as my estimate for the true mean. 3, would it be appropriate to use a normal distribution to model the sampling distribution of X bar? Well, I remember from the last unit that my sampling distribution being normal has to do with the central limit theorem and my sample size. So n is greater than or equal to 30, which means the central limit theorem applies. So yes, it is appropriate to use a normal distribution to model the sampling distribution. 4, what condition must be met to calculate the standard deviation of the sampling distribution? Okay, well, there's 3 conditions that we check. We check random condition, we check large counts condition, which in this case would be n is greater than or equal to 30, which means that the only one that is left is the 10% condition. Okay, well, let's check that. N would be all Oreo cookies. So it is definitely reasonable to assume that 30 is less than or equal to 1/10 of all Oreo cookies. We could get a little bit more specific and say all Oreo cookies made in this batch, all Oreo cookies that were in the store, but I think in let's just go general and say all Oreo cookies, and yes, definitely 30 is less than or equal to 1/10 of all Oreo cookies. So then this is where the bulk of our notes come in, and this is where it's going to be really helpful for you to hit pause and fill in the information on your own timeline. So how I would recommend you do question 5 is to watch me go through the whole thing. Like, don't even pause it at this point. Just watch me go through, and then at the very end, pause and go back through and write all this stuff down. So, what is the formula for calculating the standard deviation of a sampling distribution? So this comes from the last unit. It is sigma sub x bar is equal to sigma over root n. But we don't know sigma. If we knew sigma, then we also probably know the true mean, and in that case, this would be pointless. Constructing a confidence interval to estimate true mu would be pointless because we would know true mu. I'm going to say that one more time. we do not know sigma. We do not know the value to plug in here. Because if we knew sigma, we would also know the true mean, and then this whole thing would be pointless. Our best estimate for sigma is this S sub x that we talked about at the very beginning of this unit. So this is the standard deviation of our sample. So our best estimate for sigma is S sub x. So we could replace that in our formula. We could say, okay, so sigma sub x bar, we're going to use this S sub x thing instead, and the formula would look like this. Well, when you replace sigma with this guy, we can no longer call this sigma sub x bar, because sigma isn't involved at all. So this is now named the standard error of x. So we can't call it sigma sub x bar anymore. We refer to it as standard error of our sample. But, another but, this creates a problem. So, this is supposed to be our formula for the spread of our confidence interval, but we don't know sigma. So we got to use our best estimate for sigma, which is this guy. But when you plug that into the formula, it creates a problem. When we use S instead of sigma, we can no longer use the standard normal curve. Now, let's revisit number 3. In number 3, though, we said it is appropriate to use a normal distribution to model our sampling distribution. That is still true. We can still use a normal distribution. We just can't use the standard normal distribution. Well, why does that matter? Well, that's where we get z critical. That's where we get our critical value. So, if we can't use z critical, what do we use? So what do we use? And this is where we meet the t distribution. If we can't use the standard normal distribution, then we use what is called the t distribution. I'm hoping that some of you guys were wondering why there were so many values on this paper if all we needed was this bottom row down here. Well, turns out to do a confidence interval for a mean, you need all of these values. This is your t distribution. And notice, instead of having a z critical here, it says t critical. So now, hopefully we're seeing it really is different to calculate a confidence interval for a mean, because for a proportion, everything's Gucci. We just use these values down at the bottom. But when we start talking about a mean, we have to use a different normal distribution because we don't know sigma. It causes problems for our calculations when we use the estimate for sigma. So if you would like the information behind that about why we need this t distribution and you want all the details behind that, I would recommend that you read chapter 8 in your book. Chapter 8 goes through and takes about a page and a half to describe to you why using the z distribution for this is the issue that it is. I am okay with knowing just this. I am okay with knowing when I use S instead of sigma, I now have to use this thing called the t distribution. So let's see how that compares with our standard normal distribution, because they're both normal distributions, so they're going to look similar. So in this first graphic, what we have is our standard normal, and he is the one that I would say is taller. So this is our standard normal distribution. It's what we're used to working with. And for what we're discussing right now, one of the most important properties of this distribution is that it has a constant shape. It has a constant shape. Well, what does that mean? That means that the standard normal distribution always looks like this. Hopefully some of you guys are going, well, what do you mean it always looks, well, yeah, like why would you need to tell us that it always looks like this? Well, turns out that when you have a t distribution, that's this flatter guy, when you have a t distribution, it changes based on your sample size. So this triangle is delta. I named my pug after this. This is delta, and it is the Greek letter for change. So changes based on sample size. So let's compare the distributions before we dive into what this really means. If I highlight my t distribution, hopefully it's becoming clear that he or she is much flatter. So it's flatter than your standard normal distribution. Then the other thing that really stands out is that you have way more data in the tails. So look at your tails on your standard normal curve. There's hardly any data there. But on your t distribution, there's lots of data in your tails. So it's no longer like a 68, 95, 99.7. It's more like a 40, 80, 100. So there would be 40% of your data here, and then 20% on the outsides, and then 10% on the outsides. So way more data in the tails. And that's what this little bubble is telling you. T distributions have more area in the tails than the standard normal distribution. But the t distribution becomes more normal as n increases. By more normal, we mean gets closer to looking like the standard normal curve. So these two pictures are trying to illustrate this idea that as your sample size increases, your t distribution starts to look more and more like the standard normal curve. So this, I would say, is a small n. This is a large n. So you can see as you increase your sample size, we take this t distribution and we start to kind of like smush it up so that it looks more like our standard normal distribution. So it literally changes based off of your sample size. So this would be a small n, and as it gets bigger, it looks more like the standard normal. Now this is a way more concrete example. So the dotted line, or the dashed line, is the smallest sample. So it has a sample of 3. It says 2 here, and that'll make sense in a minute, but this would be a sample of 3. Then the gray line is a sample of 9, and look how much better or closer it gets to the standard normal curve. So as you increase sample size, your t distribution gets closer and closer to looking normal. There is a different distribution for each sample size. So literally, when we talk about the t distribution for a sample size of 10 looks different than the t distribution for a sample size of 11, looks different than the t-distribution for a sample size of 12. You're seeing that reflected in this pink table. So this column here has to do with sample size. These are the critical values that match this sample size. And the reason why all of these critical values are different is because each one of them represents the distribution that matches your sample size. We specify the t-distribution that we're using by giving its degrees, of freedom. So we shorten that down to DF, and that is your sample size minus 1. So notice we describe our t-distribution by its degrees of freedom. So this column here on the left-hand side says DF. So the last part of this lesson then is to find the t critical value for each confidence level and sample size. So our first one is a 96-degree confidence level based off of a sample size of 22. Okay, well we need to calculate degrees of freedom. That's 22 minus 1, which is 21. So we come to our pink table, we find degrees of freedom, 21, and then we slide over until we're above a 96% confidence level. So 21 and 96 is right here. So notice the 96 is at the bottom of your table and the degrees of freedom is on the left. So our t critical value for this sample is 2.189. Okay, we want a 99% confidence interval for an SRS of 10. So in this case, our degrees of freedom is 10 minus 1, or 9. So I come to my degrees of freedom column, I go down to 9, and then all the way over to 99. So that's going to be 3250. And these gray areas really do help you keep track of where you're at. So for instance, over here, 9 is in the gray bar, 1 above the bottom. And then I can just go down to 99%. So the critical value for this sample size is 3.250. So I just want to state one more time that for each sample size, your distribution looks different. It is a normal distribution. It's just a t-normal distribution. So a distribution for degrees of freedom of 2 looks different than the degrees of freedom 9. And that looks different than the standard normal curve. So these represent all the different kind of distributions there can be. Okay, last part is this little bubble here. Before I forget, I just want to highlight one last time that you're finding a t critical value. So we used to be finding a z critical. This time we're finding a t critical. When the specific degree of freedom does not appear on the table, use the biggest degrees of freedom available that is less than your desired degrees of freedom. So let's see exactly what this means. we want to find the critical value for a degrees of freedom of 58. Well, we would have to have several pages of these tables if we listed the t-distribution for every single sample size up to 1,000. So they give you the degrees of freedom for every one from 1 to 30, and then from there they start to change, and instead of going by 1, it goes by 10s or 20s or 100s. So 58 is not on here. 58 is not on here. So I do degrees of freedom is 58 minus 1, which is 57. That is not on my pink paper, so I use the closest one below 57. So that would be 50. So degrees of freedom is 57, comma, use degrees of freedom equals 50. So this is 95% confidence. 50 is 2 below the gray bar, this gray shaded area. So I go over to 95. 2 below would be 2.009. So 2.009. Okay, 90% confidence interval. Degrees of freedom for this is 973 minus 1, which is equal to 972. So I have cut the table down here, and I'm looking for 972, but my only options are 100 and 1,000. So that means we need to use degrees of freedom of 100 instead of 972. And even though that's a lot different, 100 is a lot different than 972, we still use this. So 90% confidence level for 100 is 1660. So the purpose of this video is to introduce to you the t-distribution and make it clear that when we find the confidence interval for a mean, we can no longer find or use, I should say, the standard normal distribution. We have to use the t-normal distribution. So if you didn't pause and write all of these down, make sure that you do that now. I'm good. Thank you. So that you have everything that you need for class time. Next time when I see you, we will actually be constructing the confidence intervals. Okay. If you made it through, proud of you, love you. Hopefully see you soon.